All right. So this is the first chapter of the organic chemistry. And most time we'll be spending time on the review the past topics. This chapter we focus on the bonding. And just start from the atomic structures. Atoms made of proton, electrons, and neutrons. A proton and neutron on the nucleus, they're both very heavy. And these two proton neutron almost have the identical mass. And the proton has a positive charge. And the proton attracts the electrons, which is small, flying outside the atoms. So that's basic structure of the atom. And since we learn about electron configurations, that start from the atomic orbital 1s all the way to the highest valence shell, the electrons on the valence shell are the most important for chemistry, for the forming bond or for the forming ions and so forth. And the electrons in the atoms move super fast, almost the speed of light. And so it's impossible to locate the electrons at a fixed point. And in the quantum physics, we use wave functions and the atomic orbital to describe the electrons. The wave function is basically a mathematical function. It describes the probability of the electrons show up in a certain distance and angle around the atoms. The wave function is a mathematical function that has a positive negative sign. And so for example, if you look at a p orbital like this, a dumbbell shape, and the nucleus is right in the middle, one half of the wave function, this area, it has positive sign, and the other have negative sign. In between, the electron density, it'll be 0. And this we call the node. The node in the bonding orbitals, it is actually very important, because node, it means electrons density 0, which oftentimes means the energy of the electrons can be much larger if the electrons exist around the node. And the square of the wave function, it shows you the probability of electrons or electron density, how dense electrons show up around the nucleus. So these are the orbitals. The sign of the wave function is important for molecular orbital theories, where the wave function can overlap, which means if in a location the wave function from two atoms, both are positive or both are negative, you get enhanced probability of electrons showing up. If the sign of wave function have opposite signs, one is positive and the other atom give you negative wave function in the same location, that means the wave function will partially cancel out, and that reduces the electron density in that area. Reduced electron density, oftentimes it means higher energy, because between the two atoms, two nucleus, the more electrons exist in between, which means high electron density. It oftentimes it causes energy to decrease, more stabilized. It promotes forming bonding. And if the wave functions cancel out, it means electron will show up less in between two nucleus. The energy of the bond will be higher. And so these are the wave functions, start from S, these are P, and these are D orbitals. For organic chemistry, since we do not deal with metals of very large radius, we all focus on the nonmetals, just a few nonmetals. So the bond more relevant in organic chemistry are the S, P, and often and rarely a D orbital might get involved. And so the covalent bonding nature is just because if two atoms share one pair of electrons, between the nucleus. When the two electrons which have opposite spin exist between the two nuclei, the electrons act like a glue. It will attract both nucleus, which are both positive, and that will make the energy decrease, bring down the energy. So if we use the hydrogen atom as a model, the two free hydrogen atoms, each one has one electron. When they approach, electrons are starting being shared between the two nucleus. The energy start decrease. And it will reach a minimum at a certain distance. Here is 0.74 angstrom, which is about 0.07 nanometer, 0.074 nanometer. At that distance, the energy becomes lowest. If the two nucleus getting too close, the repulsion between two nucleus become significant, and you can see the energies start going up. So the optimal distance between the two nucleus, it is the bond valence, is where the two nucleus become stabilized by the shared electrons. So electron pair bring two nucleus together. It is nature of the covalent bonding. And the covalent bond, because the atom has different degrees of attraction to the outer electrons, which we call electron negativity, the bond oftentimes is polar. Unless in the single bond, in this one bond, the two atoms are identical, then we have a purely non-polar covalent bond. Most cases, we get a partially polar bond, which depends on the difference in the electron negativity between two atoms. And so because difference in the electron negativity, so for example, between the two carbon atoms, they are identical atoms, so the electrons equally shared is a non-polar covalent bond. But most often, when the carbon form bond with the other atoms, the difference in the electron negativity will make the electron not equally shared. High electron negativity atoms will pull the electron closer, so make that negative charge. And the low electron negativity atoms will have a partial positive charge. And this arrow is in physics showing the bonded dipole. And this kind of arrow bond dipole, it shows from the positive charge point to the negative charge. Carbon-oxygen bond is a very common covalent bond in organic compounds, same as the carbon-carbon bond. Sometimes the organic compound form a compound with a metal cation, and in that case, so here the carbon form a bond with a lithium atom. Between these two, the carbon has a higher electron negativity. So the lithium has a positive charge and the carbon negative. The bond dipole point to the carbon atom. This is the organic ionic compound. The difference in the electron negativity causes a difference in the bond polarity. So basically here is a scale for the most common bond that we see in our everyday life in organic chemistry. Start from the purely covalent carbon-carbon bond, progress to the more polar carbon-oxygen, nitrogen-hydrogen bond, and lithium-carbon bond, and so forth, until the big difference between the two atoms, it causes electrons transferred. The electron will be lost from the low electron negativity metal to the high electron negativity chlorine and give us ionic compound. So that's the polar. We have different degrees of polar bond. In organic chemistry, how the molecules, how the compound react has a lot to do with bond polarity. isomerism in organic chemistry is very significant. It's one of the fascinating facts of the organic chemistry, because organic chemistry is focused on the compound that is based on hydrogen and carbon. And the carbon form bond between another carbon or some other nonmetals. They have a multiple possibilities to form bond. So for example, here, we have a 2 carbon, 6 hydrogen, and 1 oxygen. Among these 3 elements, it can actually form 2 different compounds. This compound have oxygen linking both carbon atoms. And whereas a different compound with the same number of atoms, oxygen linked with 1 carbon and also bond with a hydrogen. So between these 2 have a big difference in the structure. And because different in the structure, the polarity of the molecule, the possibility of forming hydrogen bonding, they are hugely different. This compound will not form hydrogen bonding, but it is polar because this carbon-oxygen carbon bond is about 109 degrees. It's a bent. That causes a molecule in a polar molecule. Where this molecule, you have a hydrogen bond with oxygen, which is capable of forming hydrogen bonding, and also being a polar molecule. So this compound have a stronger intermolecular force than the we call it isomers. And you can see the much higher boiling point and so forth. This compound also have better water solubility because it can form hydrogen bonding with the water molecules. And of course, the structure difference will cause them different naming. This is alcohol, and this is ether. And you can see there are many other cases have isomers. So this is this molecule. We have 4 carbon, 8 hydrogens, and it has 3 compounds where there's carbon-carbon double bond. And you can see each structure is different from the others. Between these 2, some of you learned organic chemistry last semester. This is what we call a trans molecule, because the hydrogen on the opposite side of the double bond across. And this we call a cis, because hydrogen on the same side of the carbon-carbon double bond. And between these 2, this will be a nonpolar, and this will be a polar molecule. They have a different physical properties, and in chemical reactions, they behave differently as well. And you can see this is another isomer, have exactly the same number of each atoms, but completely different structure. And this is a polar molecule. And also, we have 2 more molecules have the same 4 carbon, 8 hydrogen. They have rings. This is a 4 carbon in a ring. This is a 3 carbon in a ring. Different stereochemistry and different structure, shape, polarity. And so organic chemistry is fascinating. Deal with a compound that is vast, and their reaction oftentimes it has multiple steps, and so that's the isomers in organic chemistry. The organic chemistry focus on the compound we call it hydrocarbon. Hydrocarbon as a compound is made of a hydrogen and carbon atoms. You have this formula. And if some of the hydrogen being replaced by the other nonmetals, nitrogen, oxygen, hydrogen, sulfur, and halogens, we get different categories of the organic compound. In such hydrocarbons and other, also with other nonmetals, the bonding pattern, it follows a simple rule we call Hank rule. Hank rule, which means for these 4 nonmetals, each typically follow the fairly permanent, fixed bonding pattern. The number of bonds for these 4 nonmetals are 1, 2, 3, and 4. So oxygen in most cases form 2 bonds. Nitrogen in most cases 3 bonds, and carbon's 4 bonds. So Hank, it represents 1, 2, 3, 4 for these 4 nonmetals. And there are some other nonmetals, such as halogen. They also behave like hydrogen, tend to form only 1 bond. Oxygen and sulfur oftentimes form 2 bonds in a compound. We have a name for those: tetravalent, trivalent, divalent, and monovalent, for how many bonds for each nonmetal can form. And with the bonding pattern, that will help us draw the Lewis structures. In organic chemistry, we're not spending too much time drawing Lewis structures because we're dealing with much bigger molecules. But drawing the Lewis structures in the general chemistry, we were taught follow certain steps. You start with counting valence electron first, and then decide which atom be the center. When you decide which atom be the center, use the Hank rule will be very helpful. So which means the atom that can form more bonds, such as carbon, nitrogen, they are more likely to be the center of the molecule. And hydrogen never be the center. Oxygen depends. Oxygen typically is not the center because it can form 2 bonds. So that's the how we draw the Lewis structures. Use Hank rule as a guidance to decide which atom to put in the middle, put the center. And so that's how we draw the Lewis structures. Formal charge. This is a topic in organic chemistry. In the chemistry, we deal with it, but not really focus too much on. It is concept we learn in the general chemistry. The formal charge is numerical value with signs. And the signs, it basically shows you either the partial positive charge or partial negative charge. And that is basically shows as a formal charge. The formal charge, it only exists in the Lewis structure. So when you draw the Lewis structure, and make sure the Lewis structure follows the octet rule, which means for the bigger nonmetal atoms, except hydrogen, the valence electrons should be 8 around each atom. When you have the Lewis structure that is following octet rule, then we can use the formal charge to decide which atom has a positive charge or negative charge. The charge affects how the organic chemical reactions proceed. It will affect how they react. In the organic chemical reactions, you will never see a positive atom form bond with a positive charge atom, because electrostatically, they are repelling each other. And so knowing the formal charge, that will guide you and help you understand why does some organic chemical reaction taking place where the others is impossible. And so that's the formal charge. Formal charge calculate based on the Lewis structure. You use the number of valence electrons for that element. This is the same as the group number. The group number, it is the number of valence electrons in the atom. So this is how many valence electrons should make this atom neutral. But in the actual Lewis structure, this atom might bond with more or less electrons. So in the actual Lewis structure, the valence electrons around this atom, we calculate like this. Basically, half of the bonding electrons around this atom, plus the electrons that belongs to that atom, the lone pair electrons. So the bonding electrons is being shared with the other atoms, and so that the bonding electron need to be divided by half. It shows you how many electrons belong to this atom, and the lone pairs it is owned by this atom. So these two combined, it shows you how many electrons are around this atom in the compound. The difference between these two, it is a charge. It is a formal charge. So if the number of valence electrons is less than whatever in the parentheses, you have negative charge, which means in this structure, this atom possesses more valence electrons than actually it should. You get a negative charge. If this number is more than the one in parentheses, that means the atom in the compound, it possesses less electrons than it should have to make a neutral. Then you have a positive charge. And positive charge we call electron deficient. Negative charge, it means electron rich in electrons. So keeping in mind, organic chemistry is highly qualitative, and we rarely use numbers. Okay, we rarely use numbers, mainly use the structures, and the electronegativity and formal charge can be very helpful too to understand organic chemistry. So example of how to calculate formal charge. So this is a Lewis structure, and we calculate the formal charge one by one. And so start from carbon, okay, this carbon. So this carbon, number of valence electrons for the carbon, it is a group number, which is 4. And then in the parentheses, half of the bonding electrons plus lone pair electrons, that should be in the parentheses. In here, we can see the carbon have no lone pairs. Okay, all the electrons being shared with the neighboring atoms. And you can see the this carbon atom has 1 pair, 2 pairs, 3 and 4 pairs. 4 pairs of electrons shared with the neighboring atoms. So there are 8 electrons. And all the 8 electrons are the bonding electrons. Those bonding electrons, okay, these are 4 bonds. Each bond have 2 electrons. We get 8 electrons. Those are all bonding electrons. Divided by 2 is the electrons being that really belongs to the carbon, which is 4. So 4 minus 4 gives us 0. This carbon has a 0 formal charge. And if you look at the hydrogen has 1 valence electron, supposedly 1 valence electron, is a group number, minus there are 2 electrons that's been shared with carbon. So those 2 divided by 1 bond, each bond has 2 electrons, divided by 2, will give us 1. And the difference between this and in the parentheses, it is 0. So the hydrogen calculated have a 0 formal charge. So the carbon hydrogen basically shows you each atom has exactly the valence electron as they should have, which will give a 0 formal charge. And finally, the oxygen. The oxygen, we use a 6, which is group number, minus half of the bonding electrons. There are two electrons in 1 bond shared between carbon and oxygen. And so that's the number of bonding electrons divided by 2. And then the oxygen have 6 unpaired electrons. So combined together, we get a -1. That shows you the oxygen should have a 1 negative charge. And that's how you calculate formal charge. The valence bonding theory, this is we learned in the organic chemistry. The main point is the valence electrons, which is the electrons in the highest shell. And that is a share with the neighboring atoms to form bond. And when they form bond, there are 2 different bonding types. One is a sigma bond, and the other is pi bond. The sigma bond is the wave function, or the orbitals have the head-on overlap. The electrons shared are right along the bonding axis, and that is what we call the sigma bond. The other very important bonding, it is a pi bond. Pi bond, it is between the 2 p orbitals. And when the 2 p orbitals parallel to each other, the wave function or the orbitals have the sideway overlap. This overlap is much weaker than the sigma bond overlap, because most electrons for the p orbital are here and here. So the actual overlap is relatively poor. But since the p orbital have both above both this location and below the bonding axis, have 2 locations to overlap, it can form fairly strong bond. But typically the pi bond is weaker than the sigma bond because the sideway overlap. That's the valence bond theory, point to the 2 types of bond. One is sigma and the other is pi bond. And so the sigma bond start from the simplest model is the hydrogen atoms. The hydrogen atom, each one have 1 s orbitals, and they form the sigma bond. Electron have a highest density right between the 2 nucleus. Yeah, this electron then have the highest density. For the valence bond theory, when explaining the bond angles in organic compound, the further development, it is about the hybridization of the atomic orbitals to explain the bond angle that is not existing in the atomic orbitals, such as S, P, or D, and because you don't see the 120 degrees or 109.5 degrees bond angle in the among the atomic orbitals. To explain that, several chemists proposed orbital hybridization theory. And the hybridization theory starts from the simplest, methane, which is 1 carbon, 4 hydrogens. The bond angle, it is actually 109.5 degrees tetrahedral. This is because among the s and p orbitals of the carbon, they form hybridization. The s orbital have a lower energy than the p orbital. And so when the carbon 2s and 2p, a total 4 orbitals mixed together, will give us sp3 hybridized orbitals. And they start from 4 atomic orbitals. Hybridization gives us 4 hybrid orbitals. And these 4 hybrid orbitals have the same energy level. So after hybridization, start from the 4 valence electrons. Those 4 valence electrons will be spread out into the 4 hybrid orbitals. based on the Hans rule. And so when the 4 electrons in each orbital, each hybrid orbital will be able to form pair with the other atom, such as hydrogen. And that way, each hybrid orbital with one single electron will be able to form 4 separate bonds with 4 different atoms, such as hydrogen. And the 4 hybrid orbitals have the same energy. We call them degenerate. In quantum physics, degenerate means they have the same energy, even though in the space occupy different location, but they have the same energy. So that's how you form bond with hydrogen atoms. And the amount of S or P factors in the hybrid orbitals, it affects the shape. In the sp3 hybrid orbital, there's 25% of the S character and 75% P character. So the final hybrid orbital is more looks like a P orbital. And this is actually how the hybrid orbital looks like. One lobe is bigger than the others because between the S and P has a 1 positive negative and overlap with the S, then part of the wave function get reinforced, enhanced, have higher electron density, and the other half become less density. So we have basically an asymmetrical dumbbell shape as compared to the P orbitals. And so with all the 4 hybrid orbitals forming bond with hydrogen, those 4 hybrid orbitals will have 109.5 degrees to each other. Okay. And in the space, if we put the center of the orbitals, link them together, give us tetrahedral shape. Tetrahedral shape, those of you made that before, it's fairly straightforward. Basically, you cut 4 identical equilateral triangle with all 3 sides equal, and you use tape them together, and you can make your own tetrahedral shape. And so those 4 hybrid orbitals, each one has 1 unpaired electron, will be able to form bond with the other atom with also one unpaired electron, and with opposite spin. You can see the spin direction have opposite. Then they will be able to form bond. The opposite spin, it is to avoid the repulsion between the electrons. The electrons both are all negative charge. Naturally, they will repel, but because have opposite spin, magnetically they can attract to each other, stay in the same space. So at any rate, when they form bond, will give us 4 single bond. Each one has 1 pair of electrons. The bond angle is 19.5 degrees. So the hybridizations are even more. There's 1 S and a 1 P orbital hybridized and give us sp hybridized orbitals. Beware, this hybridization, it looks like a P orbital. Actually, it is 2 P orbitals together. It's 2 P orbitals together. I'm trying to use my pen. Let's see. My pen is not actually working. This is actually 2 of the sp hybrid orbitals together. One looks like this, and the other looks like this. So each one is a sp hybrid orbital. And since they share 1 nucleus, overlap and becomes this. So that is the sp hybridized, is a 1s with 1 p orbital mixed together. It can also have the 1s with 2 p orbitals, and that will give us trigonal planar, which is 120 degrees bond angle. And this is because you have 3 hybrid orbitals. This is one of the sp2, and here another sp2, and here one more sp2. These 3, when they share the same nucleus, it'll give you this layout. And the sp3 hybridization is when you have just like the methane we just talked about. 4 hybrid orbitals together give us the tetrahedral bond angle. We also learned about the sp3d and sp3d2. Those are d orbitals getting involved, and each one has its own shape. In organic chemistry, we rarely deal with these 2 hybridizations. So just move on to next. So that's the hybridization orbitals. This is supposed to be in-class practice, but we do have answer key in the end. So we move on with the different hybridizations. The hybridization, as we learned about the Vespa series, the Vespa series and orbital hybridization has direct connection. When we take a look at the loose structures and find out how many electron groups on the central atom, and that actually will tell us what is hybridization. 3 electron groups on the central atom. That'll give us trigonal planar. And the hybridization, it is sp2 hybridization. And this sp2 hybridization, basically you have the 3 sigma bond. And those 3 sigma bond, each one sp2, so the angle is almost 120 degrees. And there's also the p orbital, unhybridized p orbital, will form pi bond. That's where the double bond comes from. The double bond comes from the sigma bond plus a pi bond. And the hybridization is, this is how after hybridization, you have a 3 sp hybrid plus a unhybridized p orbital. And when they form bond, are those the hybrid orbitals? Sp hybrid orbitals form sigma bond. So each carbon has 3 sigma bond with 2 hydrogen and without a carbon. And then the unhybridized p orbital will have a sideways overlap, form the pi bond. Each p orbital has 1 unpaired, and when these 2 electrons have the opposite spin, it'll form the pi bond. The single bond have a free rotation, but when you form pi bond, which is low energy, it basically stabilized the p orbital parallel to each other, which, as a matter of fact, it inhibit the rotation along this bond. When there's a single bond, it has free rotation, but with a pi bond, the rotation becomes difficult. So first we have sigma bond. This is all the gray bond are the sigma bond. Yes, questions?
Professor, on the previous slide, when it came to like the hybridization, why was it that one of them, it said this is not affected? Go back one more. Like, yeah, so why is it where it says like the 2 pieces, this orbital is not affected? Why is that?
Which part?
Like in the green, where your mouse was right there, right there, Why is it that this orbital is not affected?
So this p orbital is not hybrid with the other, with s. It's basically remain pure. not hybrid.
Why is that?
Oh, it's just not been involved.
Okay.
It's like it's a bunch of people. Half the people get invited to the party, the other not invited. So they're not invited will remain unaffected.
Okay.
Yeah.
Thank you.
You're welcome. And then pi bond. Okay, the pi bond are where the p orbitals. Okay, these are from the unhybridized, the unaffected. Okay, these are unaffected p orbitals. They have a sideway overlap, form the pi bond. Okay, this sideway overlap brings down the energy, make it more stable, which means if you try to rotate along this bond, it will the energy will increase, which means it's going to be difficult. So that's why the double bond or rotation along the double bond, it requires high energy, is more difficult. This is the reason why when we see the cis and trans isomers, each isomer at room temperature, it will stay unaffected, will not easily rotate and convert to the other. And cis will remain a cis compound, trans will remain trans, unless we heat up the temperature to very high. The high temperature will allow the bond to rotate, and eventually, whichever lower energy will have more percentage. But that's the story later. We might get into that. So that's the pi bond. Today we only have this much time, so we will stop. In organic chemistry, among all the hybridizations, especially the sp, sp2, sp3, sp2 and sp3 are the most common. And for the chemical reactions, sp2 is more frequent involved in the chemical reactions. We call them unsaturated, and because they are able to add more unsaturated, you can add more stuff, more structures, more atoms to the structure. And the sp2 hybridization, so it's kind of a rehash on the sp2 hybridization. And for the sp2 hybridization on the carbon atom, it will have the 3 hybrid orbitals. It has 3 hybrid orbitals. Because there are 3 orbitals get hybridized, 1s and 2p. So after hybridization, we get 3 hybrid orbitals. These gray are the 3 hybrid orbitals. And those 3 gray hybrid orbitals have an angle of 120 degrees, or we call it trigonal planar. And there's a 1p orbital not hybridized, the red and blue. Red and blue is just show the sign for the wave function is plus minus, but it is a 1 orbital. So this layout is kind of reminds us of the sp3d hybridization, but it's quite different. Okay. sp3d, it is those five lobes, each one is 1 hybrid orbital. But here, the sp2 hybridization, the red and blue are come from 1 orbital, the p orbital. And this p orbital perpendicular to the sp2 hybrid orbitals, which are in 1 plane. So that's the hybridization sp2. And the sigma bond come from between the carbon-carbon and the carbon with some other atoms, such as hydrogen here. So these are the sigma bonds. For this smallest sp2 molecule, it has 5 sigma bonds. And there's a double bond between carbon-carbon. The first bond is a sigma bond between carbon-carbon. Each carbon uses the sp2 to form bond with the sp2 of the other carbon. And there's one more bond, the second bond in the double bond come from the pi bond, the p orbital parallel to each other and overlap, have a sideways overlap. So the electron density is mainly here, and these two overlap. So that'll give you the pi bond. The rotation. Rotation, if the bond has only single bond, which means have only single bond, you can freely rotate. So this bond, hydrogen can freely rotate. CH bond can be freely rotating. But when the bond is double bond, the pi bond, which is orbitals overlap, and it requires p orbitals to be parallel to each other. So between this chunk and this chunk, it cannot freely rotate, because if you rotate, the p orbital no longer parallel, and the overlap or the wave function overlap will become worse. Energy will increase. So there's an energy barrier for the rotation because the pi bond. And so that's why the cis and trans isomers, they are fairly stable and cannot easily convert to each other. The sp hybridization, it comes from the among the three p orbitals, one of the p orbital is hybridized with the s orbital. And so these, this is s and p, these two hybridize. The hybridization gives us two sp hybrid orbitals. And because the energy of the s and the p, s is lower than p orbital. So after hybridization, the hybrid orbital, the mix, its energy is in between. So you have energy fairly low, two hybrid orbitals. And there are two p orbitals not be mixed, so these will not be affected. In the later stage, when they form bond, the hybrid orbitals will form the sigma bond. And the remaining two p orbitals, two of the p orbitals, will form two pi bond. And that is the bonding between the carbon and carbon. You have a two pi bond plus one sigma bond. So that is how the, with the hybrid orbitals and the unhybrid orbitals all together mixed, looks like complicated. This is the one sigma bond between the carbon and the hydrogen. Okay, and then between the carbon-carbon, this gray are the hybrid orbitals. You have one gray come from this carbon, and the gray from the other carbon, and these two overlap, give you the carbon-carbon sigma bond. Its orbitals head-on overlap, not sideways. And there's the last one, also sigma bond. Then you can see the two p orbitals. This is one p orbital, and parallel with the p orbital from the neighbor carbon. So between these two have the pi bond. And so this and this, the red overlap and the blue overlap together, it is one pi bond. And there's another p orbital, the kind of horizontal p orbital. This p orbital and this p orbital parallel to each other, form another pi bond. So that's how the hybridization forming the triple bond molecule. So if you compare all three hybridizations, and you can see first of all, the bond angle is very different. The bond angle here, this is the sp3 hybridization, tetrahedral, 19.5 degrees. The actual angle is a little off, which is very normal because this carbon has a full bond that is not quite the same. This carbon has a one carbon-carbon bond and have a three carbons hydrogen bond. So the bond angle is close to 109 degrees, not quite exact. And this molecule, the sp2 hybridization, so this bond angle is 120 degrees. Last one, sp hybridization, this angle is linear, it's at 180 degrees. And you also notice the bond length quite a difference. Single bond is the longest. Double and triple, you can see the triple bond is shortest because there are 2 pi bonds. The sharing more electrons, it brings the 2 nucleus closer to each other. You have a stronger bond and shorter bond length. The bond energies is very different. It is parallel to the bond length change. The shorter bond length, you have a higher bond energy, stronger bond. And then the molecular orbital theories in organic chemistry, we actually don't use them much in the organic chemistry, but it's good. We have a quick kind of flash review on the molecular orbital theories. The molecular orbital theories are actually more scientific, more rigorous. It's based on quantum physics and really mathematically compute how does the wave functions come from different atoms, how much they overlap, and what will be the energy of those overlaps will be. So the basic idea is it depends on how the waves combine together. The wave function will have positive, negative, and when the wave function from different atoms overlap, the sign of the wave function it affects how the combination of the wave function will be. When the 2 waves have the same sign in the same location, the wave function reinforced becomes stronger. When in the same location, the 2 wave functions from different atoms have opposite sign, like this. One is positive combined with negative. And then when these 2 come together, in between the 2 nucleus, there will be location when the wave function perfectly cancel out. The perfect cancel out will give a wave function equals 0, and that is a node. Node means high energy, where the electrons do not show up between the 2 nucleus. And when the electrons do not show up in between nucleus, then the 2 nucleus has just a repulsion between these 2 positive charges. Energy be higher. And so the wave function overlap reinforced, we call it constructive interference. The interference is a physics term, and those of you who learn some physics, you've probably seen the demo about how the waves interfere. And the waves interfere, they can reinforce or cancel. And when they cancel, the waves completely destroy each other. That's what we call destructive interference. In physics, in optics or sound study, interference can be very useful. For example, we can use interference, the destructive interference, to cancel out noise. We can design an earplug that is perfectly cancel out noise come from the outside. That is use the counter or the we call it anti-phase combination of the 2 sounds. They can cancel out each other. But for the atom's atomic orbital wave function, it matters about how the electrons show up. When the wave function's constructive interference, you have a large electron density between the 2 nucleus, which means it is help forming the bond. If between the 2 nucleus have 0 electron density like this, then between 2 nucleus, there will be no electrons in between, and there will be repulsion, and energy will be higher. So wave interference among the atomic wave functions, it is can have the 2 outcomes. And so that's basically the basics of the molecular orbital theory. 2 wave functions, when they interfere, you can have the constructive, which is low energy, molecular orbitals. And also you have the wave function, the destructive interference, and it causes energy goes up. In between the nucleus, 0 electron density, you have 1 node. This is the molecular orbital that is of higher energy. And so the low energy molecular orbitals, because the energy is lower, those unbounding electrons, whatever the two electrons come from, the two hydrogen, they will populate, they occupy the low energy MO first. And since there are only two electrons, those two electrons will occupy the low energy bonding orbital first. And there will be no electrons occupy the antibonding. This is a good situation. You have overall a stable combination. And so the molecular orbital form bonding, you have both bonding and antibonding. That is very different from the valence bond theories. The hybridization and the electrons just overlap, form bond. In molecular orbital theory, it's not that simple. There are antibonding situations. It depends on if there are more electrons in the bonding than the electrons in the antibonding. If there are more electrons in the bonding, you have the overall stable situation, a low energy molecular orbital. If there are electrons in the antibonding, that is not favorable for the stability of the bond. And so that's basically the molecular orbital theory. And it can be more complicated. These are shows you just visually good idea how the actual MO looks like. And so this is a molecule that is CH3Br. We call it methyl bromide. And this compound have the high energy, among the high energy molecular orbitals, there are bonding molecular orbitals, and there are also the antibonding molecular orbitals. Okay, the antibonding, we're talking about, this is one atomic wave function. It's all combined. There's another one. Between these two, the bromine and the carbon, there's a one node. You can see there's a one node. So that makes the energy higher. Whereas in this bonding molecular orbitals between the bromine and the carbon, there's no node here. There's no node here. There's node right here, but that is, it is because the similar to the p orbitals. P orbitals have a one node right around the nucleus between two half wave functions. But this node is not really the node for the bond between the carbon and bromine bond. And so these are the antibonding MO have the node, which is 0 electron density. And anyway, the MO in the real organic chemistry, you might see some advanced publication articles when they discuss stabilities, chemical reaction, reactivities. They will use the molecular orbital to explain this, but we rarely in organic chemistry really use the molecular orbital theory. And so when we deal with pi bonds, okay, what we see over there in the past is a sigma bond. Okay, we have a sigma bond in the MO series. This is the pi bond according to molecular orbital. The pi bond is very similar to the hybridization between two p orbitals and overlap. But under molecular orbital theory, even between the two p orbitals, they are parallel. The interaction, the interference between these two orbitals have two possibilities. One is the wave function have the same sign, to form bond. Okay, so for this, it is when you have the p orbitals. This is p orbital from one carbon. This is p orbital from other carbon. And they both have, this is red and this is blue. And red and blue. So when you have these two p orbitals, Above the atom, both have the red, which or positive. Okay, if you define the red as positive, then they have the same sign above the nucleus. And the underneath are the both negative. When you have this sideways overlap, you have the reinforced positive above the nucleus, the two black carbon nucleus. And underneath, both are blue. So this is the constructive interference. You have a lower energy as a bonding orbital. Bonding MO is low energy. And so because the sign is the same, above the carbon atom, they reinforce and give you a low energy bonding orbital. If the p orbital have opposite sign, okay, let's say opposite sign, these two p orbitals, and above the carbon have opposite sign, then the interference is destructive. In between the two p orbitals, there's a 0 electron density, and we call node. Here is a node. We have a node. It's actually we call nodal plane. Nodal plane. Around this whole area, electron density is absolute 0. And since there's no electron between two nucleus, this situation is a high energy MO, molecular orbital, and it was called antibonding. So the energy is higher. That's the pi bond in the MO theories.